Yeah, hi everyone. I should probably start with a small disclaimer here saying that this is a practice talk and not the real talk, and that's because I'm really bad at practicing talks. And I thought if I would record this talk, I would at least put more effort into practicing it. So in any case, let me today talk about customer ratings, letter grades, and other types of rankings using deep learning when class labels have a natural order. So yeah, many real-world prediction problems have ordered labels. Here are a few examples. For instance, Amazon customer reviews from 1, 2, 3, 4 to 5 stars, credit risk ratings, damage assessment of infrastructure, plant disease and other types of disease, and the popular Likert scale for customer satisfaction. Yeah, and let me tell you a little bit more about these ordered labels. And in particular, how are these ordered labels different from conventional class labels? And also, we often refer to these ordered labels as so-called ordinal labels. Yeah, so to understand this a little bit better, let me give you first an example of classification. So here you see three different iris flowers: setosa, versicolor, and virginica. And the task here in a classification context is to predict what type of flower something is that we observe. And notice that there is no ordering. So we can't really say setosa is less than versicolor or something like that. I mean, we can assign integer labels like 1, 2, and 3, but still there is no ordering information. We can't really say setosa is less than versicolor and versicolor is less than virginica. In contrast, in regression contexts, we have usually a numeric scale, a continuous scale even. So here in this example, we have something like 1 ice cream scoop, 2 ice cream scoops, and 3 ice cream scoops. And we can say that 1 ice cream scoop is of course less than 2 ice cream scoops, and 2 ice cream scoops is less than 3 ice cream scoops. And notice also that the distance between 1 and 2 ice cream scoops is the same as the distance between 2 and 3 ice cream scoops. And we can also define, let's say, 1.5 or 2.5 or 2.75 ice cream scoops. So this is usually a continuous scale where we have identical distances between these intervals. Now, in contrast, there is something called ordinal regression, sometimes also called ordinal classification, that sits just in between regular classification and regression. So here we have also class labels. So here I picked 3 movies that I watched in the past, and I assigned 3 different labels to it: the sad face, the neutral face, and the smiley face here. And we can then also assign, of course, our integer labels. And this looks maybe at first glance like a typical classification problem, because we can consider 1, 2, and 3 as unordered class labels. But of course, there is also an order, right? So we can say that the smiley face is farther away from the sad face compared to the neutral face, and so forth. So in fact, we can think of these labels as class labels, but with an additional order information. And also notice that these distances are arbitrary. So in contrast to regression, I can't really define the distance between 1 and 2 here. And it's really tricky to compare the distance between 1 and 2 to the distance between 2 and 3. It's kind of like arbitrary. So the question you might ask now is, can't we just use a regular classifier for these ordered labels? The answer is yes, but it is not ideal. So why is it not ideal? It is not ideal because all wrong predictions look equally wrong to the classifier. So why is that? Let me give you a concrete example. So let's assume we have a prediction problem and the true label is the sad face here. So this is the label that is correct if a classifier predicts this label. But now assume the classifier predicts this neutral face, which would be a wrong prediction. Or another scenario would be where the classifier predicts this happy face, which would also be a wrong prediction. And both cases are treated equally if we compute the loss in a regular classifier. So the classifier really doesn't distinguish between those two and assigns the same loss to these two wrong predictions. But yeah, this smiley face should be more wrong than the neutral face, right? Because it's farther away from the sad face. And regular classifier don't consider this, and we can actually build better predictive models if we would consider this. And like I mentioned before, there are really a lot of problems in our real world where we have such ordered information, and it would be great if we could take advantage of that. And in fact, we can get much better predictive performance using ordinal regression models rather than regular classifiers. So ordinal regression models are those models that take advantage of these ordered labels. So now, how can we design an ordinal regression model that takes into account this ordering information? So we could, for instance, use something we are already familiar with, and that is binary classification, classifying whether something is, let's say, 0 or 1, or yes or no. And so in this context, we can use something called an extended binary classification framework. So let me explain what that is. So consider we have an input image that we want to classify, and this is from a so-called aesthetics data set where we have aesthetics labels, possible labels in a rating scale from 1 to 5. And we put this into a neural network. It could be any type of neural network, a CNN, an RNN, a multilayer perceptron, and so forth. And now at the output layer, we have binary classification tasks. So for example, the first output node could be asking whether the label of that image is greater than 1. So it's a binary classification task because the answer is yes or no. And similarly, we can do that for the other labels. So we can have rating greater than 1, greater than 2, greater than 3, greater than 4. So each output node in this neural network is now a binary classification task. And if we have such a setting, we can actually obtain the label by summing all the yeses that the network would predict. And by that, we can build an ordinal regression model. So for example, here, the predicted label would be 3 if the first output of the first node would be yes, and there would be another yes, and then a no and a no. So we add the two yeses and add a +1 and arrive at this predicted label 3. So in this case, we have now an ordinal regression model. And something like this was implemented, for example, in this paper I have here at the bottom, where the researchers implemented this in the context of image classification with convolutional neural networks. So while this method had a very good predictive performance, there was one little issue with this method, and that is rank inconsistency. So what is this rank inconsistency? So consider a case where you have this prediction task and the rating for the first output node is yes, the rating for the second output node is yes, and then you have a no, and then you have a yes again. So the predicted label here might be correct, let's say it's 3, but you have some paradoxical statements. So you have a network that predicts that the label is greater than 4, but it is not greater than 3, which kind of like doesn't make sense. So we have worked on some research projects where we tried to address this rank inconsistency issue. So we have two methods we developed for that I want to briefly outline here, because we found that addressing this rank inconsistency issue helps with improving the predictive performance. So one method we call Coral. It's short for consistent rank logits, which we have published last year in pattern recognition letters. And we have also a new method called CORN, which stands for conditional ordinal regression for neural networks. So how do these methods work? In a nutshell, so Coral is based on weight sharing in the output layer, and we have a mathematical proof in the paper showing that this guarantees rank consistency. CORN, on the other hand, achieves rank consistency by applying the chain rule for probabilities and creating conditional training sets. So the advantages of Coral are that Coral is very easy to implement, and it has a reduced effect of overfitting. And it's pretty fast too. So we think the overfitting reduction comes from the fact that we have this weight sharing constraint in the output layer, which kind of acts as a kind of like a regularizer, forcing the network to be simpler, which makes it also fast. And if you have a task that is very complex, you have a small training set, it can be an advantage to use, let's say, Coral. On the other hand, for Corn, it's also easy to implement, but because it doesn't have this weight sharing constraint, it allows the network to have a higher complexity or capacity, which means that the network can, let's say, be more flexible in terms of function fitting. So, and we found that this can often lead to a better predictive performance. In any case, because this is a very short talk, I'm skipping over the mathematical details, but you are welcome to read the papers if you're interested. And now for the remaining few minutes, I'm going to show you how we can use these techniques in practice. Yeah, and we can convert a classifier into a Corn model in just 3 lines of code, which is really amazing. So I'm not going to show you, though, the whole working code example because, yeah, it's a short talk. But if you are interested, I have full working examples for tabular, text, and image data here on my website that you can check out. So there's pure PyTorch code and also pytorch-lightning code. But let's, for simplicity, consider that we have a PyTorch implementation of a neural network. It could be a CNN, a recurrent neural network, or a multi-layer perceptron, and we have an arbitrary number of hidden layers here. What's interesting, though, here is only the output layer, which we have to change. So what we do is we change the number of classes in the output layer to number of classes -1. So why is that? And we can leave it like it is, but it would be redundant. We would have one extra class. Because if you recall, when we had our binary extension framework, we had these binary questions, rating greater than 1, greater than 2, greater than 3, greater than 4. So if we have 5 class labels and we answer the last one, rating greater than 4, as yes, then this would imply that we have 5 labels. So we can reduce the number of classes by -1 here. Another small change we can make here is replacing the cross entropy that we usually use for training a neural network for classification by this Corn loss that I implemented here in the Coral PyTorch package. And then the last change would be how we convert the predicted logits into the class labels. So instead of using the regular argmax that we use in a regular classifier, we would also use a function that I implemented here in this Coral PyTorch package, which is called Corn label from logits. And yeah, like I said, if you are interested, I have the full code examples here on this website that you are very welcome to check out. And if you have any questions, also, please let me know. File an issue on GitHub. There should be a discussion forum on GitHub as well. So please, don't hesitate to reach out if you have any questions or you want to collaborate or need any help with that. So with that, the acknowledgements. So I want to acknowledge Wenji Kao, Shintong Shi, and Vahid Miralali, with whom I worked on the papers for Coral and Corn. So they have been a great help, helping me all along the way. So this was really a team effort. And with Wenji, Shintong, and Vahid, I think we had a really good collaboration where we had lots of productive days and weeks or even months spending coding and doing research on this project. I also want to acknowledge people from Grid AI and pytorch-lightning who helped me a lot with being or becoming a better coder, like helping me especially with the pytorch-lightning implementations of both methods, which I can then also conveniently run on Grid AI on multiple GPUs. So maybe like a small announcement to make, because it's just a coincidence, only a few days away. So on February 25, my new book comes out. So if you are interested in my new book, you can find more information on my website. And I also have all the code examples available on GitHub. So with that, if you want to reach out, I'm more than I should active on Twitter. So please feel free to reach out on Twitter or write me an email. And also if you want to find out more about me for some reason, you can also find more about me on my website. So with that, thank you for listening. So this would be now the time for questions, but since this is like a practice talk, there is no audience, but please feel free to leave a comment on YouTube. I'm probably going to upload this on YouTube at some point, maybe in a few weeks. So thank you for listening, and please ask me any question you like.